Welcome to the Insightful Professor. Today's topic is aggregate operations. In this video, we will introduce a concept of grouping and a category of functions that operate on the groups that we define. The operations we introduce are called aggregate operations. The functions that we apply to each group of rows are referred to as aggregate functions, although sometimes folks call them group functions. The ANSI SQL standard supports several such functions, and we're going to introduce the functions that are commonly used. Because these functions are part of the SQL standard, we'll demonstrate them using two different ANSI SQL compliant relational database products, Oracle Database and SQL Server. We do this because these two products illustrate how the functions operate, but there's a little bit of a difference in the treatment of these functions between the two products, and we want to bring those subtle differences to your attention. To concentrate on the concept of grouping and aggregate functions, we again apply these operations to a single table. That table is one that you should be familiar with by now, assuming you have watched earlier videos on the channel. That's the good old course table. So let's identify the functions we'll be looking at. Now first we start off by indicating that an aggregate function operates on a group of rows and generates a single row in response to each group to which it's applied. This is in contrast to what's called a scalar function or an individual function that operates on a one-to-one basis. A single value is passed into an individual function or scalar function, and a single value comes out. So for each row, the function is applied one time. But with aggregate functions, you could have many rows, a group of rows, against which the function is applied, but always a single value is returned regardless of the size of that group. Now, aggregate functions also have this feature where the data type of the column which is passed as an argument determines the data type of the output or the result. It will be the same data type. We'll say much more about that as we go along, because that really is the focus of the subtle difference between the treatment of these aggregate functions within Oracle and the aggregate functions within SQL Server or DB2 or some other ANSI SQL compliant systems. So the functions we'll be examining are listed on the screen here, and you can see that we have sum, average, max, min, and count. So let's get underway and take a look at an example. The sum function returns the sum or total of the values in the column that's specified as the argument. So in this example, we're passing C lab fee, which is a numeric column defined in our databases as a decimal, and that becomes the argument to the sum function. Now, because this is a deriving of a new value, we're actually not taking the C lab fee value directly from the database and inserting it right into our results set or displaying it on the screen. But what we're doing is kind of massaging that data in some way. C lab fee is being pumped through the sum function, and the result is not the actual lab fee, but it's the total or the sum of many lab fees. So this is a derived value. And as we've stated in an earlier video, derived values don't necessarily get a meaningful column heading. So therefore, we're employing the ability here to rename by using the as keyword and then putting our quoted string, which will be a meaningful, hopefully meaningful, and descriptive column heading. Additionally, we say that the aggregate function operates on a group of rows. The way we're identifying the group in this particular example is to use a predicate in the where clause that says C department is equal to CIS, and we're going to identify just those rows. So let's take a look at this in our database. I'll start off with Oracle, and before we actually run this query, what I want to show you is what is the content of the course table, but more specifically, I'm going to return the rows such that all of the rows that have the same department will be shown next to one another. This is essentially the idea of what grouping accomplishes for us. So here we had said order by C department. So notice all of the rows with CIS are next to one another in the result set. Likewise, all the rows with philosophy are adjacent to one another, as are theology. Now, let's concentrate on these CIS rows. The CIS rows, we have 6 of them. the example that we're going to run says let's select the sum of the lab fee from course where the department is CIS. So rather than operate on all of the rows of the table, we've identified these 6 rows as the rows that will constitute the group of rows whose lab fee values will be passed as input to the sum function. So observe then what we will be doing is adding up these 6 values, 100, 50, 0, 0, 100, and 500. That should give us a total of 750 when we apply our predicate. Let's go ahead and give it a try. We'll say take the sum of the lab fee. And at first I'll run this without renaming to show you what happens. We'll do this from the course table, and again we'll identify our set of rows or the group of rows with the predicate C department is equal to CIS. We fire it up, and sure enough, we get that 750 that we anticipated getting. So that's good news. Now, notice that the column heading here, what Oracle did with this particular tool called SQL+, was to actually use the expression that was evaluated to produce the value, or some portion of the expression may be the case, as we'll see in later situations, but it uses that expression to derive what the column heading will be. So in this particular example, that's not too bad. But let's take this and run this in a SQL Server database and see how SQL Server responds to this. So we go over here with SQL Server and we'll paste it. And now in SQL Server, we'll run the same query, again, without renaming the column. SQL Server gives us the same result of 750, but observe there is no column heading presented here. That's how SQL Server Management Studio, as a front-end tool, handles this situation with a derived value. So let's go back and change this to agree with the example, and we'll call this total fee, putting into quoted string. We'll execute this, and now we have a much more meaningful or useful column heading in our result. Let's go back with Oracle, and what we'll do is we'll take this query and then return to Oracle to show you how Oracle deals with the renaming. And we get the same result. We get the column heading now being much more meaningful than what Oracle provided to us by default. Now, in our Oracle database, C lab fee is defined as a decimal, and credit, another numeric column, which we'll scroll back and just visit here, is defined as an integer, because we don't have like a 3.5 credit course. We have 3 credit courses, we have 6 credit courses. Let's look at how the database treats the function sum when applied to an integer. I'm going to say select the sum of cred, and again, give it some kind of a more meaningful or descriptive column heading from the course table where the department is equal to CIS. Again, we'll target the same rows, but this time the argument to the function is an integer. Okay, one thing that I've noticed over the years that you have to do is you have to spell the column names correctly. Anyway, let's go here. I just wanted to point that out to you. So here we're selecting the sum of the credit, which we saw, and we're all 3 credit for CIS, and there are 6 courses, so not surprisingly, we get the 18. Notice the display doesn't look any different here for the 2 columns. But let's take this into SQL Server. And with SQL Server, we'll go ahead and we'll apply this sum of credit, which is an integer, and see what we get. And now we get 18. Remember, a moment ago, we had our number which was shown as a decimal. It had 0.00, and that's because lab fee is defined as a decimal. Here, credit is defined as an integer, so notice there's no decimal point, no zeros that follow. So keep that point in mind. It's going to become much more important as we go deeper into these numerics. It's not going to make a big difference with sum, because whether you add up all values that are decimal but have no decimal significance in terms of digits that follow the decimal point, or whether you add up just integers, the results will effectively be identical Just how they're rendered will be different, but the results will be identical between our two different systems. But when we start to deal with other functions, we're going to see a change in the behavior. Now let's return to the presentation and say another thing or two about sum. The ANSI SQL standard specifies that the result of the sum function must be within the range of the source data type. Now, integers can be fairly large, but they do have a limit. So the ANSI SQL standard talks about numeric data with two slightly different formats. One is referred to as exact numeric, and the other is kind of an approximate numeric. With exact numeric, the system talks about, or the standard talks about, representing values exactly. The approximate numeric, suppose you took 10 and divided by 3. Well, the answer is not exact. It's 3.333, and no matter how many 3's you put on it, you haven't quite reached the exact value. It's not achievable. So what happens is the ANSI standard makes a distinction between the two types. Now, in this case, if the source is exact numeric, such as an integer or a decimal, the result is also exact numeric. And if it's decimal, it has the same scale, the same precision. What we're concerned with here is, suppose you have integer as your data type being passed to the sum function, and these values are already rather large integers. And when you perform the sum, the total that you produced exceeds what can be represented with the integer data type. Well, that's a concern that we have. So what we say is it's probably a good idea to consider using the cast operator or cast function and explicitly casting the column which will be passed as an argument to convert it or treat it as though it were a different data type. So if we were to cast the integer as decimal, we might be able to represent a larger range of values with decimal and then do a sum of those values, or a floating point, for example. So that's something to consider depending upon the nature of what you're working with. Okay, let's go one step further now and look at the average function. Well, with the average function, this is going to return the average of the values taken from the specified column, the column passed as an argument. The value can be thought of as being computed as the sum of all of the values in the column divided by the number of rows whose values were passed to the function. Not the full size of the table, because if you have a where clause, then in the case of our example of C department equals CIS, there were only 6 rows that participated. So we would divide whatever the sum of the 6 lab fees is by 6, the number of rows participating. Average also applies only to numeric types and to the date time types that are classified as intervals. Now, in this example, what we're doing is we're taking the average of the lab fee, a decimal, and again, renaming it, and we're doing it from the course table without a where clause, so we're targeting all of the rows in the table. So let's go ahead and see how this one behaves in the database. We'll start off here with SQL Server, and we'll say, let's take the sum of, I'm sorry, not the sum, this time we're into average. AVG, average of lab fee, as, and I'll just call it AVG fee, from course, and again, we'll omit the where clause and go against the entire table. So let's fire this up, and we get 110 point and a whole bunch of zeros. Well, if we take this to Oracle, let's see what happens. Let's go back to Oracle with the same exact query. Apparently I didn't grab that, so let's copy that to the clipboard, come back over, and I'll paste it. There we go. And I get 110, but again, because there are no significant digits following what would be the decimal point position, that is not shown as a decimal number using this particular tool without additional formatting specified. Okay, so that's decimal. What if we were to try something a little bit more interesting, like let's take and select the average of the credit, and we'll call this AVG credit, and this is an integer column. And let's do this from course, and to make it even more interesting, we'll pick a subset of rows where the department is equal to PHIL, just the philosophy courses. Now, remember, credit is an integer, and we're selecting from the course table just the 4 rows that qualify as philosophy department sponsored courses. So the expectation would be, according to what the ANSI standard says, the result of this computation is going to be an integer. But look what Oracle produces. See, what we have, we might want to take a closer look at the credits that are actually part of this table for the rows that we're considering in this particular example. What we have is 3, 3, 3, and 6. Add that up, and you get 15. How many values are we dealing with? We're dealing with 4. 15 divided by 4, well, comes out to 3.75, but this is not an integer. Let's go back to SQL Server and give it a try there. Same query, same data, very interesting result. 15 divided by 4 is 3, because 15 is an integer, 4 is an integer, and the result must be an integer. So what we have here is SQL Server and some other systems such as DB2 are respectful of the exact data type of the column passed as an argument. Within the table, cred is defined as a small integer. So it's an integer. Whole number cannot have any fractional component. The result is such that during the computation to arrive at the average, SQL Server preserves, say, the integrity of credit as an integer and shows the result as an integer. Oracle, on the other hand, says once I've pulled it out of the table and I'm doing this computation with that integer, I'm just going to treat it as my own proprietary data type called number. And what happens is, says you divide 15 by 4, the real answer is 3.75. The trick here is that if you were to then take this value and insert it into a column defined like credit as an integer, Oracle would then convert this to an integer to respect the data type. So Oracle respects the data type when you store the value, but kind of forgets about that when you're using it in computation. That's kind of interesting because here's the same exact table definition, same exact table data content, same exact questions being asked, and we get 2 different answers. That is pretty exciting, maybe pretty scary. So you have to be aware of how the systems treat the data. This is why I wanted to use these 2 database management systems to illustrate the behavior of these operations, because there's a very noticeable difference with Oracle than what we would see with DB2 or SQL Server. Now notice this problem gets even worse if you want to think of it as a problem, such that if you took the 375 and stored it in a table where it was stored in an integer column, it would become 4. But if you took the result from SQL Server, which produced an integer of 3, and then stored that in an integer column in a table, it would be 3. So they start to separate even further. So it's one of those things you want to be aware of. Very tricky stuff. Okay, so hopefully that was an eye-opener for you and makes you aware that you want to pay close attention to the definitions of your table and respect the data that you're dealing with. Now, this also raises the issue of using the cast operator. Let's go back and take the SQL Server where we did the average credits, and we're going to try it a second time. This time, we're going to do our second attempt and say, give me the average of the casting of the credit as a decimal. And as we do that, let's see what we have. So here we preserve the integer integrity. Here we take the integer, treat it as a decimal, and then take the average of the decimal values. Let's go ahead and give that a try. And what do we get? We get the 3.75 that we got with Oracle. But we have to explicitly say, treat this integer, or these integers that we're taking, treat them, by using the cast operator, as a different data type, such as a decimal in this example. And that will allow us to preserve the same result. Now, the reason this is important is I know many companies operate more than one database management system. They're not entirely a SQL Server shop. They're not entirely a DB2 shop. We're not entirely an Oracle database shop, but they might have different systems that they run which use different database management systems. So one client that I have runs applications with Oracle and also with SQL Server. They have to be very aware of how the data columns are defined. So if you define your columns as integer and you want to get the same result in a query where you're using a function such as average, you have to take this extra step of using something like explicit data type conversion with the cast operator. So if you write your query with the expression as shown in the second step here, then it's going to produce the same result with Oracle and SQL Server and DB2. Let me just confirm that for you by taking the query and going back to my Oracle database and dropping this in. Okay, one more time. There we go. Fire that up, and sure enough, with Oracle, it doesn't matter which expression I use, I get the same 3.75. But the point is, if I use this expression here with SQL Server, then I'll get the same result as Oracle. If I use this expression here with SQL Server or DB2, I'll get a different answer than what I got with Oracle. So keep that in mind. Subtle point, but extremely important. So that's one of the main reasons I wanted to use the two systems to demonstrate these operations. Okay, maybe you want to take a deep breath and kind of let that sink in. Okay, let's go back to my presentation. We've mentioned that there were a few other functions. Let's take a look at the max and the min function. And this query is pretty exciting because we're going to do a few things here. Here we're saying we're going to show you the min and the max, which accept numeric, date time, or character arguments. You can mix your data types. You can have anything effectively. It's not limited to just numeric data. The max and min also respect the data type of the argument. So keep that in mind when you're looking at min and max against numeric data or date time data. It's not going to convert the data for you. It's going to respect the data type. That's not so much a big deal, but that's just kind of a little footnote to be aware of. Now, this query, what's really exciting about it is it demonstrates that you can use more than one aggregate function in a query against the same column. Furthermore, it demonstrates that you can apply aggregate functions to more than one column, all in the same query. Wow, that is so exciting, right? Just calm down and take it easy, okay? Now, let's look at what we're doing. If you think about max and min when talking about numeric data, something like smallest and largest seem very descriptive. This is the smallest, that's what the min produces. This is the largest of the values, that's what the max produces. But those labels don't seem as meaningful when you're talking about character strings or if you were talking about date time data. We're not saying, well, this is the smallest name and this is the largest name, or this is the smallest date and this is the largest date. It makes more sense to kind of put them in an ordinal type of relationship and say this is the first and this is the last. Remember in the example when we were talking about using a relational operator of greater than back in an earlier video, and we talked about CNAME greater than hedonism. Well, we weren't saying we're looking for a course name that is actually superior in some way to this particular name, but lexicographically or alphabetically or in dictionary order, what follows hedonism? Well, that's the same idea here. When you're using min and max with character data or date-time data, which is actually chronological, then thinking about it as first and last makes much more sense. So those are the labels we give here to describe the output of what those functions produce with the different data types. Well, let's take a quick look at this. We're going to have the min and max lab fee and so forth. Let's see how it behaves. Okay, I'm into Oracle. Let's take a look. We're going to take the min lab fee as smallest fee. Then we're going to take the max lab fee as the largest fee. And then we'll apply the min and the max once again, this time to character data. So we'll take the min CNAME, which again is not the smallest, but more appropriate to think about it as the first name, and then the max, not the largest when we're talking about a character string or when we're talking about date time, but think more appropriately as being in an ordinal relationship, what is last, alphabetically last, or appears, say, at the end of the dictionary, for example. And we limit this once again to a subset of the rows in the table. The group consists of just the courses sponsored by philosophy. And here we go with our answer. For completeness, we'll fire this up against SQL Server, but we shouldn't see any difference there. The difference really comes about when we're dealing with the numeric data. So here we have the smallest fee, the largest fee, and it's a long result here with this tool, so I'll scroll over, show you the first name and the last name. But we have the same output as produced by Oracle. So nothing there to be concerned with. Okay, so now that's the min and the max. Back to our presentation, see what else we have. Well, what happens is there's a special keyword that can be used in our query as an additional argument to an aggregate function. This is called distinct. We've already had a taste of how the distinct keyword works when we apply it to a column list, that is a name of columns in the select clause. What we're doing here is we're applying it to the values that are passed as input to the aggregate function. Instead of taking all of the lab fees, if any of the lab fees are duplicates, the distinct says, well, we already saw that value, we're not going to use it a second time. So for example, if you have a value of 100 that appears in 2 rows, distinct says only apply the value of 100 to this aggregate function one time, not 2 times. So it removes the duplicates of the values being passed as input to the aggregate function. Take a quick look at this one. It's kind of interesting when we consider that we do have some duplicates in the course table. Take a quick look at the course table, just to refresh you on that. Well, we'll do it here in Oracle. Okay. We'll select asterisk from course, and what I'll do is I'll order by lab fee so that we can actually see what the lab fee values are. And we'll see that there are many zeros, there are many 50s, there are many 100s, multiple 200s. But now, the example we're looking at says let's focus on just one department. So let's take a look at everything in the course table, but we're going to limit the result to a group of rows that satisfy the condition of C department equal to CIS. Now, let's take a look at what we've got. We have 2 instances of 0. So using the sum, not going to make a difference. If you add 0 1 time or 2 times, it's not going to affect the result of computing a total or a sum. But observe that the value 100 does appear multiple times. So when we take the sum and apply distinct, we'll add the 100 only 1 time. So let's take the query and say let's select the sum of lab fee from the course table where the department is equal to CIS. And we get 750 because we did not use the distinct yet. So now let's take and go select the sum of distinct C lab fee from course where the sponsoring department is CIS. and now we get 650. And the difference is precisely 100, because that 100 occurred twice. When we used distinct, we only included it or passed it in to the sum function one time. And the behavior is exactly the same with SQL Server and DB2. Excuse me. Now, the count function. We mentioned 5 functions we were going to talk about. Here's the 5th one. But this one, you get a little bonus. There are 3 flavors of this. So we have count asterisk, count and supply a column name, count and supply the column name using the distinct keyword. So we'll explain each of the 3 flavors or 3 varieties. Count asterisk looks a little different than the other aggregate functions because this doesn't take the actual name of some column. Asterisk basically says, give me all of the rows. I don't care what's in any of the column. It doesn't even look into the columns. It counts the number of rows in the group. So if we say select count asterisk without a where clause, we're saying how many rows exist in the table. The table is treated as the entire group. If we say count asterisk and put a where clause, the where clause identifies a subset of rows, and what we're asking for here is how many rows are there within that subset. Pretty straightforward. When we use the column name, this is where it gets a little bit more interesting. In another video, we talked about missing information and the null value. So if you have a null value within the column, what this will do when you put the name of the column is to count the non-null values in a selected column. And finally, if you use distinct, it again kind of removes the duplicates for computation purposes or consideration purposes here and counts the distinct non-null values in a selected column. So there's no difference between the first 2 forms if you're selecting from a column that does not have nulls. But if the column does allow nulls, then these 2 operations here of count asterisk and count putting the name of a column can yield a different result. So we'll take a closer look at that within our examples. Okay, so count asterisk, as we said, doesn't actually look within the columns. The result is always going to be an integer. It's not influenced by the data type of any column because effectively column names are ignored. So in this case, I'm saying select count asterisk as, and I'm renaming it as how many, and notice the where clause is identifying the Department of Theology. Excuse me. Okay, so let's go ahead and say select count asterisk from course where, and we put something like C department is equal to theology. And when we do that, we find out that there are 4 rows in the table that satisfy this condition. We could think of this condition as identifying a group of rows, and what has happened is we said how many rows are in the group. That's effectively what we're doing here. Okay, let's change it a little bit and say select count asterisk from course where C department is equal to CIS, and we get a different answer because now we're dealing with a different group of rows. The rows that have the CIS value in their C department then have the count asterisk applied, and the answer becomes 6. So that's the basic idea on the count asterisk. I believe that's pretty straightforward. Now, the count distinct, excuse me, count distinct is used to determine the number of unique values that exist in the column name that we specify immediately after the distinct word. So down here we're saying count distinct C department. So when we apply the count function to C department and inject the distinct keyword as an additional argument, it will only count each department one time regardless of the number of instances of that department within the rows of the table under consideration. And in this case, in the absence of a where clause, we're looking for everything within the course table, all the rows. And there are 14 rows, and we know that we have rows for CIS, rows for philosophy, rows for theology. So what's going to happen is when we fire this up, we're going to count each non-null value, in this case, the C department value, only once, regardless of the number of occurrences. So let's go ahead and say select, and within parentheses we put the word distinct, not outside. It's an additional argument. Sorry, we have to have a function to put this to. Count distinct C department from course, the entire table. Notice it comes up and tells me 3. This is interesting, tells me that there are only 3 different values within this column. Remember, we know there are 14 rows, but it doesn't count CIS 6 times, it counts it once. It doesn't count philosophy 4 times, counts it once, and so on. This is somewhat related to something we looked at earlier. Let's consider the idea of saying, let's identify the departments in the course table. So by simply saying select C department from course, we see all 14 rows represented. Right? There's no where clause to filter. So what happens is CIS appears multiple times, duplicates result. Remember, we said that we can use the same distinct keyword that we're now looking at, except put it to remove duplicate rows by putting it before the columns that we are selecting. So select distinct C department from course, and now what we get is only CIS once, only philosophy once, only theology once. So let's take a quick look at what we've done. The count distinct, put the name of a department, tells you how many different departments sponsor courses. Down here we see select distinct C department tells you which different departments sponsor courses. What are the names of those departments? So there is some kind of a relationship that we can say might exist between these two. So pretty interesting stuff. Let's take a break from the course table for just one moment. Remember in the video called Missing Information, we saw that the staff table has one row with a null value in the department column. Just review the content of that table quickly. So select asterisk from staff. Now, Da Vinci has a department which we've not explicitly specified as we have with the others. This is actually the null value. So what we want to look at here is how this particular column is going to be affected or behave when we use the aggregate functions. Let's try a simple query here. ename happens to be the primary key or the unique identifier of this table. A little odd, we're saying no 2 employees can have the same name, but it'll serve to satisfy our purpose here. We're going to say select count ename from staff. And when we do this, we get a value of 9 because there are 9 non-null values in the ename column. The similar result that we get with select count asterisk tells us there are 9 rows in the table without looking within any of the columns. So if you query a column that is non-null, such as ename, or say count asterisk, which says don't even look at any of the columns, just tell me how many rows, you should get the same result. Let's take a look at the DEPT column where we know Da Vinci has a null value. So let's say select count DEPT from staff, and what we have is 8. Da Vinci's row is not counted because when you supply a column name as an argument to the count function, it counts only the values that are not null, the non-null values in that column. So Da Vinci has null, we didn't count his row. Another interesting thing is to say let's count distinct ename from staff. And because ename is the primary key, we get 9 distinct values. when we say select count distinct and we supply DEPT from staff, we get 4 values. Let's quickly revisit the staff table and focus on the DEPT column to see what those 4 values are. Well, here you see theology, there's 1 value. Here you see philosophy, there's a 2nd value. Math, engineering, 4 different values. The value for Da Vinci, which is null, was not counted. So when you select distinct and apply it to a column that can contain nulls, select count distinct DEPT, what happens is the null is not counted and you get the distinct values that are non-null within the column. So it's an interesting little aside that you want to be aware of in terms of completeness for the behavior of the count operation, and also going back to the treatment of nulls. Just very quickly, I want to show you as a reminder how nulls are rendered when we go into SQL Server Management Studio. So here we could say select asterisk from staff and fire this up, and what we get is when we see Da Vinci's row, it actually puts out this little visual aid, this eye catcher, NULL. Notice that's not a character string, quote, NULL, quote, such as we see, quote, PHIL, quote. This is not a character string. It's just a visual aid, a visual signal rendered by the front-end tool of SQL Server Management Studio to highlight or emphasize the point that the null value is present in that particular position. By default, Oracle SQL Plus does nothing like this. However, SQL Server Management Studio with SQL Server does this, but also if you were to go to Oracle's SQL Developer, you would see something comparable to that in the result. So anyway, that's just a little aside, a little bit of a reminder on the treatment of null values, but we've extended it a bit here in the context of aggregate functions. Okay, back on the slide, we want to make one more point regarding something we can do with our functions. And this pertains to arithmetic expressions. See, the aggregate functions can be used with arithmetic expressions to have the system be able to develop or express more and evaluate more complex type of calculations. So here we're showing 2 examples which look fairly similar, but we're going to make the distinction clear. Sum of lab fee plus 25 alters the argument that's passed for each row. Instead of simply passing the lab fee from a row, we are also passing the lab fee plus $25 added to that. So this is done on a row-by-row basis. The other thing that we've shown is to pass from each row its lab fee, and then after all of the lab fees have been totaled or summed, we then do a one-time addition here of 25. So regardless of the number of rows participating, 25 is added one time. This shouldn't be confusing if you've looked at the video on expressions or if you're comfortable with general arithmetic operations. But keep in mind, you have capabilities such as this, which also are pretty neat in terms of extending the features or capabilities in general of aggregate operations. The concept of forming groups, we've not really done it as formally as is done with aggregate operations. What we've done is we've identified a subset of rows from the table through the use of a predicate or complex predicate, perhaps with a where clause. We do that and we extract a subset of rows. That row is then treated as the group against which the aggregate function is applied. We have a better way of doing that, as we're going to see in a moment. Because our concern is, suppose we want to have different groups. Suppose what we wanted to do was come up with something like, and we'll give you an example right now, a group of rows defined as being courses from a particular department. So for example, how many rows are there in the course table such that the department that sponsors the course is theology. That is, how many theology-sponsored courses are there? We get 4. We form the group of theology courses. We could also go ahead and come up with a query that says, well, how many philosophy-sponsored courses are there? And it's a separate query. Within that query, we form a different group. And we can continue this for each such department that we know to exist. So I have 3 departments. I have 3 distinct queries, each one defining its own group, and then each one applying the aggregate function to those groups. Well, that's not all that bad, but they are 3 separate executions. Furthermore, suppose we were working at a larger institution that had more than 3 or 4 departments. Suppose we had 50 departments, 100 departments, 500 departments. Then we have 50, 100, or 500 different queries that we have to consider when we want to perform the operations. And if there's a department that I don't know about, for example, here I've shown theology, philosophy, CIS. Currently, management does not sponsor any courses, yet it's capable of doing that, and it would be valid because there is a row in the department table for management. Suppose management suddenly started sponsoring courses. I would have to write a new query that says C department is equal to management. If I was unaware that management started sponsoring courses, and I didn't write such a query, I would be overlooking that department. The technique I'm going to show you next provides a great way to avoid that little incident, and it's much more efficient because the system is taking a look at the big picture to begin with and forming groups for us. We're going to extend the SQL syntax here to include an additional clause. And the clause is group by. So this allows SQL, or the system, to form the groups for us. It's kind of a logical formation. It doesn't alter the database because, again, we're doing this within a read operation, within a select operation. So we're forming these groups logically, and then for each group that the system forms, based upon the criteria we specify here in our where clause and in the group by, what we'll see is the aggregate function will then be applied. This is really a nice feature of SQL. Very powerful, very expressive, and we don't really have to do much work to accomplish this. So here's the general idea. The grouping column that we have in this example is C department. We're going to have all of the rows with the same C department value bundled together or grouped together. We can then apply the aggregate function, and what the system will do is it will apply this aggregate function. In this example, that being average of the lab fee, it will apply it to each group that the system forms. Now, what happens is when we select the data or retrieve the data, we are also permitted to include any columns that are specified in the group by in the select list. The select list can identify only properties or characteristics of the group. For example, if I say average lab fee, but I don't group by department, and I don't group by anything, I'm not permitted to select any other columns because those column values don't apply to the group against which the aggregate was applied. Okay, let's take a look at this one in action. Okay, here what we're looking at is select the average lab fee, and I'll do the grouping, but I'm not going to select the column just yet. And I say group by C department. When I group by C department, remember we have 3 different groups. We have 3 different departments, CIS, philosophy, and management. So 3 groups are formed, and we get the average for each one of those groups. That is really neat. Now you see the value of being able to select C department, because which department has the 125 as the average? Which has the 8750? Which has the 110? We don't know that. from looking at this output because we've not identified the department mapping to the particular average lab fee. This is why being able to select columns that are characteristics of the group, that were used in forming the group, is so powerful and so useful to us. So now, when I select that column together with the aggregate, I get some kind of descriptive information that says, the 125 is the average lab fee for the CIS sponsored courses. Very, very useful. One other thing we'll do here is take this query and just show you one other little neat thing that you can do with it. Suppose I wanted to arrange the result in such a way that I wanted to take the average lab fee that was computed and order the rows for presentation purposes according to the value in there. Well, I could say order by, and I can use this new name that was assigned. And now I'm getting, with the default ordering, ascending sequence, I'm getting the 8750, the 110, the 125 in that order. And likewise, I can go ahead and make that modification to include the grouping column, making the query much more informative to whoever might run it. So there we go. So I can order by and use the name of the column in the order by clause. Very nice capability that's presented to us here. Now, with the group by, we can talk a little bit more about the overall structure of the query. The where clause can be used to include or exclude certain rows from consideration prior to the formation of the groups. What we're talking about now is there is an order in which the various clauses are evaluated. And what we're saying is the where clause will be evaluated before the groups are formed, and hence before the aggregate is applied to each of the groups. The order by clause we just indicated could be used in the query to control the presentation of the result, and this is evaluated effectively at the end. Syntactically, it will appear at the end of the query when we write it. Select, from, where, group by, and then order by. Order by will appear always at the end. But the way these things are evaluated is what we want to give some attention to. And we'll take a closer look at that as we move ahead here. So let's consider the current query here. We'll take this query, we'll go into the database, and we'll kind of dissect it. We'll examine the details of exactly what is happening, at least from a conceptual perspective. Whether this is the exact physical sequence of steps is not relevant, because what we really want to do is understand logically or conceptually what's happening here. So let's take this query, break it apart, and explain the steps by which we can understand it to be executing. So here's the query. Before we run it, let's take a look at what's happening. We have a where clause, and what does the where clause do? The where clause serves as a filter to determine which rows are going to participate in the next step. When we have simply a where clause, select from some table where, what it determines is which rows will appear in the results set. Well, here what's going to happen is this determines which set of rows will then go into the group formation process. Then, once we have that, the group formation process occurs, and let's explain what's going on there. We already have a feel for this. If we were to say select C department and average lab fee from course, so select C department, average lab fee from course, group by C department, what happens? Well, when you have the group by, remember the idea is this is kind of suggesting that behind the scenes, the system is going to select the rows from the table and order by C department. This may actually happen, but the decision as to how the grouping process occurs is made by the optimizer, and the optimizers are constantly being improved in relational databases. So don't count on grouping actually causing a sort or an order by type of operation to occur. That may be what happens, but it could be something different. The researchers at these companies that develop the optimizers are pretty sharp, and they come up with some interesting ideas. But here's what happens logically or conceptually. We say order by department. That is effectively what the group by department can be thought of as doing, getting all of the rows here in order. Okay, now here are all the CIS, here's all the philosophy, here's all the theology, and so on for every department. The department rows are separated in a sense. They are grouped together. Now this is detail or individual rows. When we do the group, this is where we get an aggregate. So when we apply a function such as give me the average of lab fee, we're going to be doing it when we have a group by for each group of rows, say in this example, that belong to the same department. So here's conceptually what we can think of happening. The group by could be thought of as causing this ordering of the rows to occur. Then we're going to say, well, I need the average lab fee. So what I'll do is I'll get the lab fee from the first row, identify which department sponsors that row. I'll remember which department. So let's go ahead and put that kind of in a little footnote. The C department is CIS. Now we'll get the lab fee. The first one is 100. Then we proceed to get the next row. First, the system will check, is the next row in the same department? Yes, this is still CIS, so we'll take its lab fee and we'll place it together with our other one. Remember, we're going to do an average, so we first have to sum. Then the next row, same department, so we take its lab fee, take the 0. Then we get the CIS for the next row. We take its lab fee as well. So we're going to add the 0 for the next row. Next row is still CIS. We take the 100. Next row is still CIS. We take the 500. Next row, there's a change. This is what might be called control break processing. The field that's controlling the processing is the field that we're grouping by or ordering by, say, behind the scenes. Once there's a change in that control field, we're certain that we will never see another row from what department we just finished with. There are no more CIS rows. There can't be because these are all in order. So therefore, there's a change. There's a control break change here. So what we do is we say, well, let's add these guys up. And when we add these guys up, what we're going to get is the 750. And we count them. There are 6. So it's going to be 750 divided by 6. There's the average. So what the system will do is it'll print out the average for CIS and what the average is. Then it resets everything. It starts all over again. So what it will do is it says we now have philosophy and get the lab fee for this new row. The lab fee is 100. And the process is repeated. And we do this for each time there's a change in this control break field, which is our grouping field. So that is conceptually what's going on. Well, let's show you what is actually going to happen here. We're going to say, go ahead, apply this grouping, and then do the average. And sure enough, what do we have? Once we've exhausted the CIS rows, we put out the average and then go and process the next department. Once we've exhausted the rows there, we put out the average and then process the next department. And it continues that way until we processed all of the groups. So conceptually, that's what's going on. Now, the query that we are looking at now goes a step further. Take a look at this guy and consider a little bit more detail. Yes, there will be grouping. Yes, there will be an aggregate applied to each group, but before the groups are formed, the where clause fires up. So when we do this, what's going to happen is we're going to restrict the groups to containing only 3-credit courses, which means philosophy, which has a 6-credit course, this average will now change. Theology, which also has a 6-credit course, its average will change. The CIS average will remain the same because all of the courses from CIS will participate because they're all 3-credit courses. Let's confirm this behavior. So a moment ago, we had the 125 for CIS, and this time we continue to have the 125. Again, as I said, no change because all rows satisfied the where clause. All rows from CIS were then passed into the group for that department. But observe philosophy, which was 8750, has now changed to 116 and 67 cents. And then likewise, theology, which was 110, is now 80 because they each had a 6-credit course, which was not considered as a result of the where clause. So hopefully that gives you some feel for what at least logically or conceptually is occurring behind the scenes. But it also says something about the order in which these events occur, or the order in which the actual clauses are evaluated. And that's what we want to take a little bit closer look at as we continue here. Now, in the next slide, what do? We say there's another little subtlety. We say sometimes when you're forming a group, right, we're going to group by, in this case, lab fee. Sometimes when you form a particular group, that group may have only one row. Do you recall some of the lab fee values that we saw? We saw lab fee values of 0, and more than one row had that. Hence, when we form a group with a lab fee value of 0, there will be more than one member. We saw lab fee values of 100 multiple times, lab fee values of 50 multiple times. But there were some lab fees, such as the lab fee of 500, which was unique. Only one course had that. What's interesting is when we say group by lab fee, and even if there's only one row that has a particular value, the group is still formed, and there's no special signal to say, hey, you got only one row in the group. We just have to understand that or recognize that that can happen. So let's take this guy and give this a try and see what we find out. So here we have the query we were just discussing. Let's go ahead and run it and see what the result produces. What we have here is we have 500 and the total credit is 3. Now this should tip us off right away that there's only one row contributing a value here. And that's because each of our courses is either 3 credits or 6 credits. So whenever we see 3, clearly there's only one course. If there's 6, there's a possibility there's one course, but possibly it's 2 3-credit courses. Let's modify the query slightly so that we can confirm the number of participants, the number of rows within the group. And we can do this by taking advantage of the fact that we can use more than one aggregate function. So what we're going to do is select not only the lab fee and the sum of the credit, but we're going to count the number of rows in the group. And we're going to do this for the courses, again, in the course table, grouping by the lab fee, and ordering by this as well. There we go. And sure enough, we see 1 for 500, 1 for 150, and 1 for 90. Now, the reason I stress this point, that there's no warning, there's no signal, there's no indicator that you have only one row, is let's take this and switch the context. Suppose instead of courses, we were looking at employees, and instead of lab fees, we were looking at salaries. So if someone was doing analysis and trying to do some kind of budget predictions, and they said, let's take the sum of the salaries, for example, or the sum of this, or average of this, then you're not exposing the value of any individual member. You're not suggesting that, oh, this is how much money Mo makes because he's the only one that satisfies this condition, or this is the salary of Larry, and so forth, because you're getting several values that are being placed together. So if you take a look at this, it's kind of interesting to note that there's the possibility here that confidential or sensitive information might be the source of what we're dealing with, and somehow we're exposing something of a sensitive nature. It would be nice, I think, if there was some kind of a warning or indicator that, hey, this group was formed with only one member, but that's not the case. So anyway, you've been informed of that. Just be aware of that behavior. Okay, let's move ahead now to a little bit more on the group by, and this is another subtle little twist in the behavior of grouping. We say sometimes the selection criteria specified in a where clause will eliminate all rows from a potential group. Well, how does that happen? Remember, the where clause is evaluated before the group is formed. Therefore, only the rows that kind of make it over the hurdle, that is, that have passed the test of the where clause, will go into the group formation process. In this particular query, we're identifying those courses with a credit of 6, which means no 3-credit courses will participate. However, we're grouping by the C department column, which would suggest we'll have a group for philosophy, a group for theology, a group for CIS. However, CIS has no 6-credit courses, so it will contribute no rows past the where clause into the group formation process. Hence, CIS will not appear as a group in the result. Now let's go ahead and confirm this behavior. So what we'll do is we'll say select C department, the average lab fee from the course table, and we'll say where cred is equal to 6, group by C department. And notice that, yes, indeed, only 2 groups are formed. There is no CIS group because no CIS rows satisfied the where condition, which is evaluated prior to forming the group, which occurs prior to evaluating the aggregate function. So again, kind of a little twist in the behavior here. Important to know, though. Now, we've been suggesting there's a specific order in which the clauses are going to evaluate. We want to take a step further here and kind of formalize this. This may or may not be exactly what transpires under the hood as the system does its thing. But keep in mind, if we understand this as being the logical order in which the events occur, it gives us a better grasp of how the query will execute and hence what it will produce, but also a better understanding of a step-by-step approach of how to write the query. So what we've seen thus far is we feel pretty confident that the where clause is evaluated first, then the group, and so forth. So let's take a look at something that gives you an idea here of why this is so important to understand the timing. Let's suppose somebody says, I want the average lab fee for courses, but I want to see it for each such department. But I don't want to see it if the average lab fee is less than 100. I only want to see those higher averages. The only mechanism that we're aware of for filtering data at this point is the where clause. However, there's a little problem here. If you were to try to run this, this will not work. You'll get a nasty error. The where clause is evaluated before the group is formed, hence before the aggregate function is applied. So logically, it makes no sense to attempt to put a condition in the where clause that checks the average lab fee against a value, because at the time that the where clause is evaluated, we have no idea what the average is because we haven't even formed the groups. So hopefully that makes sense. Try to run this query and you'll confirm that it will not work. So what we have is a special clause called having. Having is somewhat similar in behavior to the where clause in that it does form a filtering process. However, it filters at a different level of detail and it filters at a different point in time. The having clause is evaluated after the groups have been formed, after the aggregates have been computed. Furthermore, the having clause generally is going to be evaluating an aggregate value. So again, it has to occur at a later point in time. Syntactically, notice that the having clause is placed after the group by. So let's take a look at what happens when we actually fire this up. So here's the query. Select department, the average lab fee from course, group by department, having average lab fee greater than 100. So the having is where we're doing our filtering or our testing. So now, notice that we have CIS and theology. Each department has an average lab fee greater than 100. If we were to take just the first 3 clauses and omit the having, that is, don't do the filter, we recognize, hey, there is a third department, a third group, but when we put the having, we filtered that out. So the having evaluates at a different point in time. Very, very important concept, because the where clause serves a certain purpose at a certain point in time. We need a different mechanism to do filtering when we're dealing with groups and at a later point in time. Okay, so that's pretty important. So here's how I describe what goes on here. This is something where I woke up in the middle of the night and I said, aha, this is the way to explain it. This makes sense. And I've been doing this for years. So a select statement has a certain syntax that we must follow. We code the select statement by saying select and identifying the columns, from identifying our source table, where indicating row filter conditions, group by if we want to form groups, having if we want to filter the groups that are formed, and then order by to control the order of the rows for presentation purposes. You cannot deviate from this. This is the order in which the clauses must be coded. It's just like understanding the grammar of your natural language. There's a certain valid way to form a sentence so that it is considered grammatically correct and people will understand it. If you shuffle things around and move the verb and the subject and put adjectives all over the place, it's not going to make any sense. You have to follow a certain coding convention, the syntax or the grammar. Now, unfortunately, that's not the order in which the events are evaluated or processed, at least logically. Here's the way I describe it. What happens is the where clause starts off first. See, I've got my timeline here, and time progresses across the screen, and you see the arrowhead showing our direction. So the where clause is done first, before the group by. The rows that pass the test of the where clause then go into the group formation process. After the groups are formed, the aggregate function is evaluated, and after the aggregate function is evaluated, you can apply having to do filtering. And remember the column rename that we've used? That occurs way near the end, just prior to order by. This raises a very interesting point, because column renaming occurs before order by has available to it the new name of the column. But any of these conditions or clauses that occur prior to the renaming process, you cannot use the new name. This is why you could not use a renamed column in your where clause. You say select from some table, and you put some column as, and you give it a new name. You cannot, in the where clause, use that new name because the new name has not been created or assigned at the time the where clause does its thing. Nor could you use it for grouping purposes and having. It has to only be available after it's occurred, and that means it's only available to the order by. That's how the game is played. Okay, this is my great inspiration, my contribution to relational database. I'm proud of it. Okay, let's go ahead. So let's look at the having clause in more detail. We understand a bit more about its timing, what it does. Now we get a better feel, I think, for how all of the pieces come together. Let's take a look at this query here. This says, let's select the department, the average lab fee from course. The where clause is evaluated first, which means no theology courses will participate. Then we do a group by, which means we're only going to have CIS and philosophy courses going into the group formation process. So we'll have two groups. And then finally, after the two groups are formed, we have a having clause, which serves as a filter for our presentation. And it turns out that of the two groups, only one will satisfy our having clause filter. So potentially, three groups could be formed. We eliminate one immediately by never putting any theology rows into the group formation process. And then after the two groups are formed, we exclude one of them by the filter in the having clause. And that's where the timing can be helpful in looking through and trying to understand a query that someone else may have written. Okay, and sure enough, there's only one group. Again, the having had two groups at that time, but the having eliminated one of them. Theology was never formed as a group because there were no rows passed to the group formation process. Even though there's only one row, let's extend this query just a little bit for the fun of it, just to show you one more little piece. Obviously, this doesn't make any sense. If we put an order by in here and say order by C department, okay, there's only one department. Or if we say order by average fee, there's only one fee. But let's put it in here just for the fun of it to show you again the details of the timing. Now notice it was accepted, it worked. So what happens is if we walk step by step through the process, step one is apply the where clause. So that means only philosophy and CIS courses go to the next step. What's the next step? Grouping. The group by kicks in, and now we group the philosophy row courses together, we group the CIS courses together. They go on to the next step. What's the next step? We compute the aggregate. We compute the average of the lab fee. Now, we've got the two groups, and we've got their averages. What do we do next? The having comes in. The having applies a filter condition. It looks at the averages and determines which of the averages satisfy the condition of being greater than 100. Turns out only one of them. We're just about ready to display, but before we do, we rename a column. That is up here. That's where the rename occurs. Now we're all set, and then we say, oh, we want the rows presented in a certain order, and we do the order by, and we use that new name, that renamed column. Now, it's not pretty because if you're programming and you don't program kind of in a structured fashion, you notice I'm jumping all about the query to show you I'm doing this. Now I'm over here doing that. Now I'm back down here. This is what programmers have typically referred to as spaghetti code because it looks like just a mound of spaghetti and you can't really see a systematic way through which you're going through the steps. It's not pretty, it's not organized. But the syntax requires that we code the clauses in this particular sequence. You must do it that way. But that's not by any means the order in which these clauses are evaluated. This is why it can sometimes be confusing to understand code for a query that someone else has written because you can't read it, oh, I'm doing this, then I'm doing line 2, then I'm doing line 3, line 4. You can't read it that way and process the data in the same way. You have to understand which steps are evaluated at which time. Furthermore, if you're writing this query, developing it from scratch, you still have to write it in this order, but that's not the way you might be thinking about what's happening. Oh, first I want to get rid of the theology rows. Then I want to do the group. And notice you're doing that in the middle of the query, but logically, those may be the first events that you're thinking about. So it's not pretty, but hopefully this will help you understand the process. Okay, the next slide, 25, what we say is a having clause can have multiple conditions connected by Boolean operators. Remember, the where clause could have complex predicates, and we use the Boolean connectors or Boolean operators such as and, we can use or, we can even throw not in there. Well, similarly, we can use the Boolean operators or connectors with the multiple conditions or predicates that we're evaluating in the having clause, and that's what we're illustrating here. Identify those groups that have an average lab fee greater than 100 and also have fewer than 6 rows. Count asterisk is less than 6. So that's a pretty neat extension to the having clause. Then we can go on and say, well, remember our good old order by can have multiple levels of ordering. We can have a primary, a secondary, a tertiary, and so on type of order. Well, we can do the same thing with grouping. This one is kind of interesting, so I'll actually run this one to show you the details. What we're going to do is group by department, and then within department, we're going to group by credit. Now, this will be important when we look at philosophy and theology, because those two departments each have courses with multiple credits. We have 3 credits and we have 6 credits. CIS has only 3 credit courses. Then we're going to apply the aggregates. Let's fire this up and see what we actually get. So what we're going to do is say, let's select C department and credit, the 2 columns by which we'll be doing the grouping, and we'll get the average of the lab fee and we'll get the max of the lab fee, and we'll also get the min of the lab fee. And again, we're giving what I believe to be appropriate names here in our rename feature. And we'll get all of this from the course table. We can't run it yet because we have to form the groups. Remember, when you're having aggregates and you select other columns, those columns can only be selected if they have somehow become a property or characteristic of the group. And we do that by saying group by C department and then cred. Now notice we can select both columns because both are in our group. Now let's look carefully at the result. There's only 1 row for CIS, and I said that's because the secondary level of grouping involves credit, and they have only 3 credit courses. But notice for theology there are 2 rows, and for philosophy there are 2 rows. The rows for theology are separated based upon credit. I have information about the 6 credit theology. I have information about 3 credit theology. And the same for the philosophy, the 3 credit and 6 credit. Notice when the aggregates are applied, the average, the max, the min, they are applied at the lowest level of detail, at that subgroup. In this case, at the credit level within the department. Very powerful capability with only a little bit of code required to accomplish this. It's very impressive if you think about what you would have to do if you were writing this by hand, writing code yourself. But these operations are very concisely expressed, but very powerful in what they accomplish. And then we take the same query and we tweak it a little bit. The original query just selected everything that was grouped. This one includes a filter for the group having max lab fee greater than 0. So let's go and apply that and just observe the behavior. So again, I'll grab my entire query, and now I'll go ahead and add the having clause, having the max lab fee greater than 0. Now it's almost the same query as what we just looked at. There were 5 rows generated. Watch what happens now. There are only 4. What we've done is we have eliminated one of the 2 philosophy rows because we said, oh, the max lab fee has to be greater than 0. Notice philosophy 6 credit does not satisfy that condition. However, the other philosophy row, 3 credit, does satisfy that. It has the max lab fee, or the most expensive column, greater than 0, so that one is retained or preserved in the output. So again, the having acts as a filter for groups, and what we want to recognize here is that when you have multiple levels of grouping, then you're filtering at that lowest level. So let's summarize what we've seen. There's a great deal of material that we presented in this video, but it's very useful material, very powerful features that we've seen of the language. So we've examined the behavior of aggregate functions in both Oracle Database and SQL Server, 2 ANSI SQL compliant relational database products. And that gave us the opportunity to see that there's sometimes differences in terms of how vendors choose to implement certain features or capabilities. So although the behavior is almost identical, there are some distinctions when it comes to working with particular data types. So aside from that point, the behavior is essentially the same. Now, we've said that aggregate functions return a single result row based upon a group of rows rather than on single rows. So many go in to the function, one comes out. Aggregate functions can be used in the select list, also in the order by and the having clauses, and we've seen that. I'm not sure I demonstrated it with the order by, but I believe you get the idea. The aggregate functions are commonly used with the group by clause in a select statement where the rows of a queried table or view are divided into groups. And then the DBMS applies the aggregate functions to each group of rows and returns a single result row for each group that is processed. If you don't specify a group by clause, then the entire table is considered the group for which the processing occurs. Now, I'm posting files with the queries that we've looked at in case you wanted to try some of these things out on your own. And you say, well, I wish he had made this little change and demonstrated how that works. Well, take the code and try it for yourself. And if you have any questions or comments regarding what we've covered or suggestions along that line, please add them in the comments section. And by all means, consider subscribing to our channel so you can be made aware of when we post future videos. Now, if you want to find the files, go to the website. This is the website that I have, and I've associated it with YouTube. And go to the Insightful Professor link in the menu and look for the file named Aggregate Operations, and you should be good to go. And once again, thanks for watching.